Welcome to Easy Academic. Today in the linear algebra series, we'll be going over Gaussian elimination. Now, Gaussian elimination extends from the idea of elimination matrices. But to understand Gaussian elimination, we must first understand what a pivot is. So what is a pivot? There are three important elements of a pivot. First is a pivot position. So the pivot position in each row is the first non-zero entry when you're reading the row in the matrix from left to right. So say we have any row R, call it Ri, in any matrix. When you're reading this row from left to right, the first value in that row that is non-zero is the pivot position. So Ri is first non-zero entry. So when we use Gaussian elimination to turn a matrix into something called row echelon form, the pivot lies to the right of the pivot in each previous row. So say we have the first row. In the second row, the pivot must be to the right of where the pivot is in the first row. So say, for example, the pivot in row 1, the pivot is the first element. In row 2, the pivot must be some value greater than 1 in terms of which element it is. Must be the nth element, where n is greater than 1. So then we have the pivot element. So with the pivot position, all we've clarified is that it's some non-zero entry. However, the pivot element is what that value actually is. This can be any value. However, in reduced row echelon form, which is an extension of row echelon form, we often find that this value is 1. Finally, we have the pivot column. So the pivot column represents the entire column where any given pivot is. Now this is important because each pivot column is linearly independent. So what does this tell us? This tells us that if we create a new matrix that only contains all of the pivot columns that are in our original matrix, we can, in theory, create the same number of linear combinations as using the original matrix. But now we have less information that's being used to get to the same number of possible linear combinations. So now that we understand what a pivot is, we can actually perform Gaussian elimination to create a matrix in row echelon form, sorry. So there's a checklist of things we want to do in order to accomplish row echelon form. So first, we want all 0 rows, so that is all rows containing only zeros. We want all of these rows to sit at the bottom of the matrix. Secondly, we want to make sure that the property above here with the pivot element, or sorry, with the pivot position, is maintained. That is, we want every non-zero in any given row to be to the right of the pivot in the previous row. And third, we want every entry that's below each pivot to be a 0. So let's work through an example of how we'd create a row echelon form of a matrix. So here we have the matrix A, which is a 3 by 4 matrix. And the primary idea of transforming a matrix to a new matrix in row echelon form using Gaussian elimination is based on the idea of matrix elimination, which you can find a video for relating to elimination matrices in the card. Now, in the elimination matrix video, we use the example of square matrices. However, uh, elimination in matrices and matrix transformations can be done on non-square matrices as well. The properties all still hold. So you can swap any two rows, you can add a scalar multiple of one row to another, and you can scale any row by a value. So step one in this example is, for convenience, we're going to scale the first row. We're going to take it and we're going to transform it to 1/2 of its original value. And that is so that we can get this first entry to be equal to 1. So that will look like 1, 1 over 2, 0, 3 over 2. The next step is to attempt to eliminate this value that's directly below this pivot. So it's important to identify that in the first row, this 1 is the pivot. And so in order for the pivot in the second row to be to the right of the first row, we must eliminate this value that's directly below it. So in order to do that, we're going to transform it by taking row 2 and transforming it to row 2 plus a scalar multiple of some other row. So we're going to take row 2 and we're going to say plus negative 1 times 4 times row 1, which more simply can be written as row 2 minus 4 times row 1. So what this looks like is row 1 again remains unchanged. Then in row 2 we subtracted 4 here. We then have negative 4 times negative 1 over 2, which is positive 2, so we add 2 here to get 5. This remains unchanged. Then we have negative 4 times 3 over 2, which is negative 6. So we have 7 minus 6, which is 1. And then the bottom row remains unchanged. Again, we want to make sure that all of the values below each pivot are 0. So since we've identified this 1 to be a pivot, this 6 must also be a 0. So we'll do the same thing with the third row, which is row 3 will be transformed into row 3 minus 6 times row 1. And here again we observe that row 1 and 2 are unchanged. And since we've now subtracted 6 here, we then do negative 6 times negative 1 over 2. So we get plus 3. This is also 5 then. We do negative 6 times 0, so this is unchanged. And then negative 6, and then negative 6 times 3 over 2, which is a negative 9, so this is 0. We now observe that in the second row, this value is a pivot. So here we can scale this to 1, like we did with the original first value, but since we observe that the value directly below it is the same, it's a lot more convenient to just keep this 5 as it is and subtract it directly. So we'll transform the third row again by doing the third row minus the second row to eliminate this value and make all values below this pivot equal to 0. And so again, the first row remains unchanged. The second row remains unchanged. In the third row, we have 0 minus 0, we have 5 minus 0, we have 1 minus 1, and then we have 0 minus 1, which is negative 1. And so this is our final matrix in row echelon form. So we observe that the pivots are 1, 5, and negative 1, and we can write this as A tilde to indicate that this is the original matrix A in row echelon form. Let's identify a useful property that's been obtained by finding the row echelon form of this matrix. So because we know that these three are the pivots, that means that there are three independent or linearly independent columns. And so what that means is that the rank of matrix A is 3. And so by using Gaussian elimination to find matrix A in row echelon form, we're able to obtain the rank of matrix A in a pretty concise way. And the rank can tell us some other things which we'll discuss further in future episodes. But if you're interested in learning about rank of a matrix, be sure to check out the video available in the card. If you have any questions, feel free to leave them in the comment section below. Otherwise, like and subscribe if you found this helpful, and thank you.